How do we minimize the risk of mid-air collisions between aircraft? And how does that change in the era of artificial intelligence and things like drone swarms? Claire Tomlin works on questions like these, and her work is now the basis of a new field of AI, in which a system automatically learns operational and control objectives from data while maintaining things like flight safety. I'm Jennifer Strong, and this is Shift.
Now here on the steering column is a device called Auto Cruise. You simply set the speed you want.
Self-driving robo-taxis are already on the road in
As the disc rotates, a mirror reflects the light in the way that depends on how the signal was recorded.
This is the 100 terabyte I present to you Electro, the Moto Man.
Ladies and gentlemen,
I would say that one of my greatest skills is my ability to interact with humans.
This episode, it's the latest installment of our oral history project.
My name is Claire Tomlin, and I'm a professor at UC Berkeley in electrical engineering and computer sciences, and I am the chair of the EECS department. My background is in electrical engineering, and I am a control theorist, which means I work on problems where we try to model a system, a dynamic system, and I'm particularly interested in aircraft and aircraft systems and air traffic control. We develop automation techniques, in a sense, trying to understand how to improve the safety of the system and maintain safety levels. In my research group, we've worked on a number of systems from aircraft, different types of aircraft. We have a lab where we fly drones. We've worked a lot with air traffic control systems. And the overall goal is, as the systems become modernized with more newer techniques, we want to be able to ensure that performance is improved or maintained. But in particular, my group has been interested in safety and understanding what safety means, understanding how to design automation which maintains safety constraints in the system. And so, for example, in air traffic control, the aircraft are guided by human air traffic controllers that are connected to the pilot through the voice command systems and radar systems, which are detecting where the aircraft are. And there's been a number of projects that have been going on for years about trying to figure out how to develop systems that would aid air traffic controllers in maintaining safety in the system, for example, in collision avoidance, but also to be able to improve the throughput of the overall system. So how to do that requires developing models of the system, that means mathematical models, and designing automation techniques that have provable guarantees about them and that are tested in various levels. So that's the kind of research we do. And I'm very excited about it. I love practical problems, and I love being able to take meaningful mathematical methods and turn them into useful practical concepts that are used in everyday life. It's daunting when you start out. And I always tell my students this because it's good to know that you're starting something that is new. By definition, you're working on research that's trying to solve things that haven't been solved before. You know, you've come out of an undergraduate program where you're largely learning about things that people have solved before. So there's this transition to a new direction. And at the time, again, kind of following along, being very practical, I was taking PhD courses, but I was also a little concerned about funding during my PhD. And I got a job opportunity to work at NASA during the summer and eventually kind of one day a week during the school year. And it was there that I got introduced to this problem where, a lot of the engineers there who'd been working on new types of aircraft, in particular, they were working on a high-speed civil transport. And that program had unfortunately just been canceled. And so a lot of the engineers were being kind of reconsidered into different areas. And the area that was the biggest and continues to be is in air traffic control, thinking about how to modernize what systems, what sensors, what techniques to modernize the air traffic control system. And so I was there as a student intern working in that kind of arena. And it was fascinating just learning about this problem. It's this incredibly complex system with lots of aircraft, lots of people in the loop, air traffic controllers on the ground getting a lot of data about where the aircraft are, pilots flying the aircraft, but, at the same time in constant communication with air traffic control. Disturbances that come up, weather, aircraft are late for some reason. So it's a system where there's a lot of moving parts, literally. And when one thinks about how do you take a system that's kind of grown up in a very manual way following the development of radar after World War II and introduce automation and do it in a way that kind of helps the humans that are experts in the system. It's not only a technical and technological problem, it's got a lot of social aspects to it. Really thinking about when you have a human-centered system, how do you design the automated components, the physical, the technological pieces so that they're safe, they perform as well as you'd like them to, but they also work well with the people, many aircraft, many air traffic controllers, many pilots, different kinds of sensors. And then as we're coming into now the last decade, really thinking about new types of sensors, which involve machine learning and AI, and integrating those in a way that the overall system remains safe and you improve the performance overall. And performance is really measured in different ways, and safety is always maintaining the constraints of the system, making sure that aircraft always stay separated from each other, making sure that you can deal gracefully when there's a problem in the system, like weather problems, like an airport is closed, things like that. I was just drawn to the kind of the immensity and the complexity and the practicality of the problem overall. I've worked on a number of different systems. Probably right now, the thing that I'm known for is not necessarily the AI component. It's earlier work that my group and I did in collision avoidance systems and how to develop mathematical models, which I would say I would describe them as they're not prescriptive. So the mathematical models don't necessarily assume something about what all the other aircraft in the system will do. Instead, you put capabilities on the other aircraft, and then you try to solve for, in designing a collision avoidance system, you design the system to make it safe despite, the worst possible actions of the other vehicles, the other aircraft within their capabilities. Now, that could be quite conservative, but that gives you as long as you trust your models about the capabilities of other vehicles, that gives you a safe solution. Now, that doesn't assume that we are assuming that aircraft are out to, collide with each other. But when we put in what are the capabilities of the other vehicles in the model, we take into account reasonable limits. So errors that might occur in sensors, for example, or, just normal variation in flight, or wind or weather that could move an aircraft off its intended path. So the idea that we introduced is to use game theory to a mathematical method which represents individual, we call them agents in a system, and represents their action space, but doesn't prescribe ahead of time what those other agents would do. And when we started working on this, most of the other techniques were prescriptive. They would say, okay, this is what these aircraft typically do. Whereas we rather took a step back and looked at the ranges of actions that vehicles could take. We've been working more and more on methods that bring in machine learning or AI into perception. Sensors on board the vehicle are getting lots of information. There's now cameras and other sensors that can be used to detect the presence of other vehicles. And then the data processing methods that are used to process the data that comes from those sensors, AI is being introduced, but not yet in the air traffic control system, since it's so safety critical and because there's still not a very good understanding about AI and its failure modes. Now, a lot of the work that my research group and I are doing has focused on, okay, if we were to start introducing AI components into aircraft and air traffic control, what are the kinds of ways we can analyze the uncertainty coming out of those AI components so that we can make good and safe decisions, so that the automation can make better decisions about what is being perceived, about, even using AI to predict the behavior. So now I'm going back to this prescriptive or non-prescriptive. Well, if you have a wealth of data now about how vehicles behave, AI can be used to take that data and provide good estimates of the predictions of what other vehicles will do. And so it's exciting to think about a future air traffic system, which is right now everything's safe because it's so tightly controlled by air traffic control. But if we're able to slowly introduce new functions that use some of these modern AI methods, how could those be introduced in a safe way that maybe allows the system to be more flexible, to introduce new modes of transportation, such as air taxis or drones into the air traffic system? So those are the kind of futuristic research concepts that we're working on. There's different interpretations of safe AI, and the perspective that I take is really based on the kind of systems I work on. I talk a lot about human in the loop or a control loop. That's because control theory is by its nature feedback. It means that, if you're designing an autopilot for an aircraft and that autopilot is basically in the cockpit and you can hit some buttons and it will guide the aircraft, the pilots can essentially be hands off. What feedback means is that the system that's been designed, which incorporates sensors and actuators, it automatically controls the thrusters and the elevators of the aircraft to maintain, for example, a constant altitude. That system is constantly measuring where it is and then using that information to update its control. It says, oh, I'm moving down a little bit because of some wind. Well, I have to, change my elevator so I come back. So that's kind of that control loop. Measure where you are and adjust your control surfaces to get you back to where you want to be. So that's the automation loop. And I think that safe AI, in the sense that I think about it, is when some of those components, the sensors in the loop, or any kind of even the decision-making components, are replaced with automation or replaced with AI, that system still has to maintain safety in all sense. And there's many different senses of safety. It has to maintain its own constraints so the aircraft stays in the sky, obviously. That's called maintaining its flight envelope. It has to maintain safety with respect to its goals. It has to stay on its path that's been prescribed to it or close to it, and it has to respect the constraints with respect to other aircraft. It has to land in an appropriate manner on the runway. So all of these impose constraints on the system. And if any part of that system is automated or uses AI, the AI you have to be able to prove that that AI will, not disrupt the system and cause it to violate its constraints. There are different definitions of safe AI, but in the end, they all come down to developing an automated system that respects constraints, and how one defines constraints is a problem in itself. As a student, one of the first things that we develop is defining the constraints of the problem and understanding whether those are hard constraints or whether they're soft constraints, and to what degree they can be violated or not is a key part of the problem. So I would define safe AI as AI which has guarantees that it can maintain constraints.
This episode was produced by me and Emma Silikans and mixed by Garrett Lang, with original music from him and Jacob Gorski. Thanks for listening. I'm Jennifer Strong.
From PRX.